السلام عليكم ورحمة الله وبركاته. يعطيكم العافية شباب صبايا. Our video for today is from chapter 30, which is about nuclear physics. So in this chapter, we are going to talk about radioactivity. In other words, we are talking about the decay of unstable nucleus. So as I mentioned, we are going to talk about radioactivity. But at this stage, you need to know the following. In general, the nucleus could be found either in stable or unstable nucleus. And this unstable nucleus will keep going in some process to be stable nucleus. So this process, we call it radioactivity, where in this process to move from unstable to stable elements or nuclei, we can see the following: emitting of radiation, and this process could be called as decay to convert the unstable into stable form. So I can summarize the radioactivity as a process that the atom or the unstable element follow to be stable element, and we can break this process into two parts, or the result of this process in two parts: radiation and new element or new nuclei. So in general, we can write our element as you can see here. X is a symbol for the element, such as, or for example, aluminum, sodium, calcium, something like that. And where the upper side is the mass number and the lower side is the atomic number, whereas the mass number is the number of protons plus the number of neutrons, where and you need to know that the number of proton is the same as Z, or the atomic numbers, or the number of electrons. Now, another form of the same element after certain radioactivity process, which is called isotopes, whereas the isotope is atom of the same element, but with a different number of neutron and same number of proton. In other words, we can change, or in isotopes, changing the number of neutrons will change the number of, or the mass number, because as you can see here, the mass number is the number of protons plus the number of neutrons. So if we change the number of neutrons, the mass number will change. From what I mentioned previously, we can summarize the radioactive as the following: is a result in a new form of atoms, where the radioactivity results having an unstable nucleus. In other words, the unstable nucleus will keep going and decaying until they reach stable element forms. Let me take another example, which is alpha, beta, and gamma. Suppose we have a radioactive source, magnetic field, and screen, as you can see here. From the first point of view, you can see three types of radiations: alpha, beta, and gamma. In general, if we have a charged particle, I mean like electron or proton, and we placed this charged particle inside a magnetic field, therefore the charged particle, and again I'm saying charged particle, will experience a magnetic force, and we can determine the direction of the magnetic force based or using the right hand rule. But we do not care about this point in this chapter. All what you need to know that if the charge or if the particle has a charge and moving inside a magnetic field, therefore this charged particle will experience a magnetic force and will deflect in certain radiation, in certain direction. So from here, alpha and beta, because they are deflected, one of them counterclockwise and the second clockwise. That means I have positive, I have two different charged particle, where gamma is moving straight line. That means it's uncharged uncharged, or there is no charge for gamma radiation. So in general, alpha particles are helium nuclei, beta particles are electrons, where gamma rays are uncharged, and they are photons. In this slide, I would love to summarize the difference between alpha, beta, and gamma, either in their mass, where alpha particle is the heavier one, and gamma has no masses, and in their energy of penetration, or in their energy, where alpha has the lowest energy, then where gamma has the highest, then beta, then alpha is the lowest one. Therefore, the radiation of penetration, or the depth of penetration of their radiation, is varying, where therefore we have to use, if we are looking to do some protection or shielding, for alpha is more than enough to use sheet of paper, for beta piece of aluminum foil, and for gamma, since gamma radiation has the highest radiation and the highest penetration, so we are going to use block of lead or concrete to stop gamma rays or gamma radiation. Now, during this decay, let us go back to our sample and denote the initial or the number of a nuclei in this sample is n of 0 or n naught before any decay. Therefore, we can calculate or measure three, or actually two main terms or parameters, where the radioactivity or the activity of this sample and the number of nuclei remains after the this decay. So the radioactivity after a certain time is given by R of 0 times exponential minus lambda times t. Here, let me remind you, or it's worth it to mention the following. T is the time, or the time that we are calculating for, and lambda is the decay or decaying constant. And please, T is a unit of time, and a unit of time, and lambda is 1 divided by unit of time. So please be careful. T, if T in second, lambda should be in 1 over seconds. If T in days, lambda should be 1 over days. The second parameter, which is the number of nuclei remains or remaining after the after time, or after the decay will be n0 exponential minus lambda times t. And here finally, as I mentioned, I have some sample of initial number before decay. And n of t is the number of nuclei remaining after the decay or after time t. Now, to calculate the number of decaying nuclei, we are going to use n decay equals n0 minus n of t, or n0 minus n of t. New parameter you need to know about the radioactivity, which is the time required to decay a sample of 50% of its initial activity, which is the half-life time. So suppose we have sample of n0, and please pay attention to this statement or this example. If I have a sample, and write it down, please. If I have a sample of n0, now if the decay, or if I'm looking for the number of remains or remaining nuclei after one half-life time, so it will be 1/2 n0. If I'm looking for the remaining nuclei after 2 half-life times, it will be 1/2 times 1/2 n0. If I'm looking for the number of nuclei, the number of nuclei remaining after 3 half-life time, it will be 1/2 times 1/2 times 1/2 n0, which is 1/8. Therefore, we can calculate the half-life time using this formula, which is ln2 divided by lambda. And you need to remember that the half-life time depends only on the radioactivity material itself. Now, we can use new term, which is the effective half-life time, where is the effective half-life time is a combination of biological half-life time and radioactive or physical half-life time using this formula. In Na22, whereas the half-life time is 2.6 years, what is the decay constant? In other words, calculate lambda. So we know T half-life times equals ln2 divided by lambda. From here, lambda equal ln2 divided by T, or by T 1/2. Please, if I'm looking to calculate lambda in unit of 1/years, keep the time here in years. But if I'm looking to calculate lambda in minutes or seconds or days, you have to convert this time from years into either seconds, days, or minutes, for example. Here I'm calculating the half-life time. Sorry, this one should be lambda instead of T 1/2. I'm sorry, it's typo error. This should be lambda. So lambda in unit of seconds, 1/seconds. Another example, for the same element, if the sample has a total mass of 200 grams, half-life time of 5 seconds, and initial rate of decay is 10 times 10 to the power 12, calculate the number of nuclei in this sample. In other words, we are going to calculate the number of atoms. So you need to use your skills back from chemistry course, where we can relate the number of nuclei or atoms with Avogadro numbers and the mass of the sample. So in other words, N equals M times Avogadro number divided by the atomic mass. Second, what is the radioactivity after 60 seconds? R after 60 equals R of 0, which is given here, 10 times 10 to the power 12 decay per second. Sorry, this one should be decay per second, times exponential lambda times T. Be careful, lambda here is unknown, so you have to calculate lambda using T1/2 equals ln2 divided by lambda. Therefore, we calculate lambda, which is 0.14 of unit 1 per second, because T here, T1/2 is 5 seconds. Take this value and go back to this formula. Number 3, what is the number of nuclei remains after 60 seconds? So N of 0 times exponential minus lambda times T. And finally, what is the number of decaying nuclei after 120 seconds? Be careful. In this part, I changed the time from 60 seconds into 120 seconds. In other words, you need to calculate N of T after 120 seconds, and you know N of 0 from part 1. So you have to use N of 0 minus N of T. N of 0 is the same, but N of T is not this one, because this one based on 60 seconds. So you have to change the time from 60 into 120. Another example, in iodine 131, which is used in the treatment of thyroid disorders, the number of nuclei remains after 24 hours is 1/4 of its original amount. This statement is kind of hint or key of my solution. Let me see what the half-life time. We know the half-life time is ln2 divided by lambda. Lambda is unknown, so we need to use another way, or to go into another way to solve it. From this statement, the number of nuclei remains after 24 hours, which is N of T, is 1/4 N0. So we can say 1/4 N0 equals N0 exponential minus lambda T. We know we can cancel out N0 with N0, take the ln for both sides. You will end up with T1/2, or half-life time, is 12 hours. I will leave this for all of you as practice. And finally, this example is for practice too. Thank you, and see you in the next, I think next meeting will be for solution of suggested problems from chapter 30. Thank you so much.